The Aufbau principle states that, hypothetically, electrons orbiting one or more atoms fill the lowest available energy levels before filling higher levels. In this way, the electrons of an atom, molecule, or ion harmonize into the most stable electron configuration possible. Aufbau is a German noun that means construction. The Aufbau principle is sometimes called the building up principle or the Aufbau rule. The details of this building up tendency are described mathematically by atomic orbital functions. Electron behavior is elaborated by other principles of atomic physics, such as Hund's rule and the Pauli exclusion principle. Hund's rule asserts that even if multiple orbitals of the same energy are available, electrons fill unoccupied orbitals first, before reusing orbitals occupied by other electrons. But, according to the Pauli exclusion principle, in order for electrons to occupy the same orbital, they must have different spins. A version of the Aufbau principle known as the nuclear shell model is used to predict the configuration of protons and neutrons in an atomic nucleus. Madelung energy ordering rule. The order in which these orbitals are filled is given by the n+a rule, also known as the Madelung rule, or the Janet rule or the Kleczkowski rule, or the diagonal rule. Orbitals with a lower n+a value are filled before those with higher n+a values. In this context, n represents the principal quantum number and the azimuthal quantum number. The values are equals 0, 1, 2, 3 correspond to the s, p, d, and f labels, respectively. The rule is based on the total number of nodes in the atomic orbital, n+a, which is related to the energy. In the case of equal n+a values, the orbital with a lower n value is filled first. The fact that most of the ground state configurations of neutral atoms fill orbitals following this n+a, n pattern was obtained experimentally, by reference to the spectroscopic characteristics of the elements. The Madelung energy ordering rule applies only to neutral atoms in their ground state, and even in that case, there are several elements for which it predicts configurations that differ from those determined experimentally. Copper, chromium, and palladium are common examples of this property. According to the Madelung rule, the 4s orbital is occupied before the 3d orbital. The rule then predicts the configuration of 29Q to be 1s22 s22 p63 s23 p64 s23 d9, abbreviated, r4s23 d9 where R denotes the configuration of R. However, the experimental electronic configuration of the copper atom is R4s13d10. By filling the 3d orbital, copper can be in a lower energy state. Similarly, chromium takes the electronic configuration of R4s13d5 instead of R4s23d4. In this case, chromium has a half-full 3d shell. For palladium, the Madelung rule predicts Kr5s24d8, but the experimental configuration, Kr4d10, differs in the placement of 2 electrons. History equals the Aufbau principle in the new quantum theory equals. The principle takes its name from the German, Aufbauprinzip, building up principle, rather than being named for a scientist. In fact, it was formulated by Niels Bohr and Wolfgang Pauli in the early 1920s, and states that, this was an early application of quantum mechanics to the properties of electrons, and explained chemical properties in physical terms. Each added electron is subject to the electric field created by the positive charge of the atomic nucleus and the negative charge of other electrons that are bound to the nucleus. Although in hydrogen there is no energy difference between orbitals with the same principal quantum number n, this is not true for the outer electrons of other atoms. In the old quantum theory prior to quantum mechanics, electrons were supposed to occupy classical elliptical orbits. The orbits with the highest angular momentum are circular orbits outside the inner electrons, but orbits with low angular momentum have high orbital eccentricity, so that they get closer to the nucleus and feel on average a less strongly screened nuclear charge. Equals the n+a energy ordering rule equals, a periodic table in which each row corresponds to one value of n+a was suggested by Charles Janet in 1927. In 1936, the German physicist Erwin Madelung proposed his empirical rules for the order of filling atomic subshells, based on knowledge of atomic ground states determined by the analysis of atomic spectra, and most English language sources therefore refer to the Madelung rule. Madelung may have been aware of this pattern as early as 1926. In 1962 the Russian agricultural chemist V. M. Kleczkowski proposed the first theoretical explanation for the importance of the sum n plus a, based on the statistical Thomas-Fermi model of the atom. Many French and Russian language sources therefore refer to the Kleczkowski rule. In recent years some authors have challenged the validity of Madelung's rule in predicting the order of filling of atomic orbitals. For example, it has been claimed, not for the first time, that in the case of the scandium atom a 3d orbital is occupied before the occupation of the 4s orbital. In addition to there being ample experimental evidence to support this view, it makes the explanation of the order of ionization of electrons in this and other transition metals far more intelligible, given that 4s electrons are invariably preferentially ionized. See also, electron configuration, valence electrons, is Wesser's rule. References: Cottingham W. N. and Greenwood D. A., An Introduction to Nuclear Physics ISBN 0-521-31969 Chap 5 Ground State Properties of Nuclei, The Shell Model, Electron Configuration from Weisant, Weinhold, Frank. Landis, Clark R. Valency and Bonding, A Natural Bond Orbital Donor Acceptor Perspective. Cambridge, Cambridge University Press pages 715-16. ISBN 0-521-83128-8. Seri, Erica, How Good is the Quantum Mechanical Explanation of the Periodic System? J. Chem. ed. 75, 1384 €85. Bibcode, 1998 JCH ed. 75.1384 S. doi, 10.1021/edo 75 p. 1384. Meek, Terry L. Allon, Leland C. Configuration irregularities, deviations from the Madelung rule and inversion of orbital energy levels. Chem. Phys. Led 362, 362 €64. Bibcode, 2002 CPL. 362 362 M. doi, 10.1016 per second 0009-2614, 02, 00919-3. Goudsmit, S.A. Richards, Paul I. The Order of Electron Shells in Ionized Atoms. Proc. Natal. Accord. Sci 51, 664 €671. Bibcode, 1964 PNAS. 51664 G. doi, 10.1073/FNAS 51.4.664. Wong, D. Pan. Theoretical Justification of Madelung's Rule. J. Chem. ed. 56, 714 €18. Bibcode, 1979 JCH ed. 56 714 W. doi, 10.1021/edo 56 p. 714. Seri, Eric. The Trouble with the Aufbau Principle. Education in Chemistry 50, 24 €26. Further reading, Image, Understanding Order of Shell Filling, Boyerens, JCA Chemistry from First Principles. Berlin, Springer Science 2008, ISBN 978-1-4020-8546-8, Ostrovsky, V. N. On recent discussion concerning quantum justification of the periodic table of the elements. Foundations of Chemistry 7, 235 €39 doi, 10.1007 per second 10698-005-2141 Y. Abstract. Kitgawara, Y. Bharat, A.O. On the dynamical symmetry of the periodic table. 2. Modified Demkov-Ostrovsky atomic model. J. Phys. B. At. Mol. Phys. 17, 4251 €59. Bibcode, 1984 JPHB. 17.4251 K. doi, 10.1088170013. Seri, E. The Trouble with the Aufbau Principle. Education in Chemistry, 24 €26. Vanquit Kenborn, LG Transition Metals and the Aufbau Principle. Journal of Chemical Education 71, 469 €471. Bibcode, 1994 JCH ed 71 469 v doi, 10.1021/edo 71p 469. External links, Electron Configurations, the Aufbau Principle, Degenerate Orbitals, and Hund's Rule from Purdue University.